In this video we are going to look at integration from first principles. From your previous studies you should be familiar with the idea that an integral represents the area on the curve. On this diagram you can see the solid line, which is a plot of a function f of x, and the shaded area represents an expression that we call an integral. We call this the definite integral of f of x, of a function f of x, between the lower limit a and the upper limit b. The formal definition of an integral involves subdividing the finite interval from a to b into a large number of subintervals. These subintervals are going to be very small, and so small that we can even look at every slice as a rectangular. And to find the area of that rectangular, we are going to multiply the length of the subinterval by the value of function f of x. And then we are going to add the areas of all those tiny slices, and we are going to form this sum, f of xi multiplied by delta xi. And now if n is allowed to tend to infinity in any way whatsoever, then the length of each subinterval is going to be almost zero, or we say tends to zero, and therefore assuming that, say, f of x is continuous, then this expression, this sum, tends to a specific or unique limit, that is I. So if our function is continuous, then the definite integral is guaranteed to exist. So we definitely will find a value, definite value for I. So if no unique limit exists, then the integral is going to be undefined. From this definition, there are some properties of definite integrals that, although they look really obvious, they are very useful in solving different problems. So, for example, integral from a to b of 0 dx is going to be 0. If a function is always 0, there is no error. This fact is really useful when it comes to very complicated integrations. Another fact is that integral of f of x dx from a to a is going to be 0, because if there is no length actually, so there will be no error at all. Then, say, if we have an integral from a to c, we always can divide, we always can split the area under the curve, say from a to c, into two areas, from a to b and from b to c. Then obviously if an integral from a to b is taken from a sum of two functions, say f of x and gx dx, so it's going to be equal to the sum of both integrals. And finally, very useful property that comes from combining this property and this one. If I will look at function f of x dx from a to a again, but I will take a kind of intermediate value b between a and a, which is a little bit artificial, but let's assume we can do that. So obviously this integral is equal to 0, and then taking this part into the right side, we are going to get our great property, which will be very useful in our calculations, that if you simply swap the limits, then integrals will have opposite signs. So we are going to use all these basic facts in our calculations. That's the end of the video, and thank you for watching.